Oh,
Yeah.
how about now? Is it better?
Yes, yes, sir.
I'm saying, is it better now?
No, no. Actually, it's a bit noisy here.
Oh, let me try to fix it then.
Yes.
By the way, how do you feel right now, Vijit?
Sir, no. Actually, not that much confident because what
Mm,
happens? Uh, actually, I told you that reason, and
mm.
however, I'm trying hard. I'm giving my best, but at the meantime, sometimes I'm feeling a bit demotivated.
Yeah, yeah, I
So,
can understand.
like, actually, I'm trying to trying to consolation myself that even if I didn't crack this year, then I might definitely crack next year. That I could release some pressure for that I can attend this exam.
Right, right. Yeah, so give your best this year also. You, if even if you try to appear next year, at least you will have some experience of how to,
Uh-huh.
yeah, sit in the
Actually,
exam and answer.
bit, sometimes I can't hear your voice. Actually, it's very noisy background because some of my neighbors playing music very
Oh,
on
I
loudly,
see.
sir.
I
You
see.
perhaps even could listen there.
Yeah, yeah, yeah. Some noise is coming. I think someone
Yes,
else
sir.
is here. Ritesh, can you just tell me if my voice is clear to you?
Your voice is definitely clear, but I can hear you due to that reason.
Okay, okay. Yeah, yeah. I see. So, Ritesh, you are joining for the first time, is it?
Yes.
Oh, okay. So this is actually our last session, and yeah, I mean, so you will be appearing for the GATE exam next week also.
Yes, sir.
Okay, okay. Yeah, I hope yeah you have covered all of the syllabus. Today we will just do problems from all the topics that we had covered in the last, I don't know, 10 12 weeks. So we have questions from maths as well as fluid mechanics that we will do today. And yeah, so I don't know if anyone else will join. Let's get started. So yeah, this is the question. You have been given f of x, which is sum of sine x plus cos x over some domain 0 to 2 pi, and you have to
Minimum value would be sir pi by 4, right, sir?
no, Vijit, you have to do the calculation and then tell me. So
Yeah, actually,
yeah,
as per my assumptions, as I have calculated by like after derivation, if we put zero, then that
hmm.
might we get tan inverse zero. Then
See, Abhijit, let's think of it in a different way. Okay, you know that sine x goes from
yes, sir.
-1 to 1. Okay, this you know,
Yes, sir.
right?
Yes, yes, sir. Yes, sir. The
Yeah.
range of sine is -1 to 1. Sine and cos
Also,
both are
same.
-1 to 1.
Yeah, 1 to 1. So this function f of x, which is the sum of sine x plus cos x,
Yes, sir.
can
Sin
act.
x is equal
Yeah.
to cos x, then if sin x is equal to cos x, then tan x would be 1.
No, no, no. Let's not go there. Let's just see that this function f of x will have its maximum value when
Okay.
sin x and cos x have their maximum value. Okay, because it's a sum of these two. So
Okay,
when
okay, okay.
this
Now got
is
it.
1, when this is 1, then you get f of x being maximum, right?
Mhm,
So this is the maximum value of f of x is 2, whereas
mhm.
it will be minimum when sin x is minimum, which is -1, plus when cos x is also minimum, which is again -1. So
Then
-2.
-2.
Yeah.
Hmm.
So, but if you say that, okay, at pi by 4, since the first derivative is 0, uh, so since the first derivative is 0 at pi by 4, you are saying that it is a minimum x. That's the answer, right? But if you put pi by 4 here,
Uh-huh.
so basically you will not get
I got it, sir.
yeah. So the point is, actually you have to check the double derivative also. So you have f of x, then you calculate f prime of x. So this gives you the condition for local maxima or minima. So if you calculate f prime of x, this will be cos x minus sin x. Okay, and you say that this is equal to 0, then that means that tan x is equal to 0.
Uh,
Oh, sorry, tan x is equal to 1. Okay.
1. So that's what I told, sir.
Yeah. Yeah, tan x is equal to 1. You are right. So tan x can take the value of 1 at pi by 4, but not just at pi by 4, okay? It can
Sir,
take the,
first one would be cos x minus sin x would be 0, sir, not 1.
right, yeah, because, yeah, the derivative you have to put to 0. Yeah, thanks for this. So, this gives you that tan x should be equal to 1, and then x can either be pi by 4 or pi plus pi by 4, because tan is also positive in the third quadrant.
Ha 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 ha. Yeah, that's why I made mistake.
Exactly. So now you would not have made this mistake if you calculate the second derivative. So second derivative of this will be minus of sin x minus of cos x, right? So you can also write it as sin x plus cos x minus of sin x plus cos x. So we know that when the double derivative at the local maxima or minima is, so these are called the critical points. So when the double derivative at the critical point is less than 0, then that critical point is a maxima. Whereas when the double derivative is greater than 0, at the critical point, it is called as the minimum. Right. So if you put pi by 4, you get a maxima actually. And if you put pi plus pi by 4, which is equal to 5 pi by 4,
Yes.
you get a minima. So the final answer has to be 5 pi by 4, not just pi by 4.
Ha, ha, ha.
Right. So yeah. So you can calculate the numerical value of 5 pi by 4. It will be some 3.92, and that is your answer to this problem. So this makes sense, right, Abhijit?
Yes, sir. Yes, sir.
Yeah. Okay. So if you have finished that question, let's see this one. And this is again, we have seen this plenty of times. So divergence of a vector field. You can
Yes,
just
sir.
give me the final answer, please.
Okay, okay.
Yeah. I'll still write down the formula for people who don't remember it.
No, sir. Never notation, I know.
Okay. Good.
6.
Yeah, but okay. In so this is a numerical answer type question, right? So you can't. If you have a calculator with you, please just give me the final thing.
4.159.
Yeah. So this is right. 4.15 is correct. You got it, Avijit?
Yes, sir.
Did you get the same answer? 4.15.
Yes, sir.
Okay. Yeah. So this is just simple differentiating all the three components.
Yes, sir. Yes, sir.
Yeah, and they're just putting x, y is equal to 1 and then getting the final answer. Pretty basic. So now let's see this one also. This is from Fourier. We have also looked at Fourier in great detail. So I think that this one also you can do. Just remember what A naught is. A naught is the mean of the function over the interval 0 to 2 pi here.
A.
Yeah, that's the right answer. So I'll just put on the formula for A naught. The here our so this function is 2L periodic from 0 to 2 pi. So 2L for us is 2 pi. And we had seen that the Fourier formula was for the constant term was 1 over 2L over integrating over the whole period. So that is 0 to 2L f of x dx. And for us f of x is x square and 2L is 2 pi. So this is 0 to 2 pi integrating over 0 to 2 pi x square dx. So if you do that, I guess you will be able to get to option A. So I hope everyone is able to do this. If so, let's move on to the next question. Okay, this one is from fluid mechanics now. So we are switching between fluid mechanics and engineering mathematics today. And these are most questions are easy because I really want you guys to have some confidence going into the exam. So please try to solve all these quickly and then
Yes.
that will yeah boost up some of your confidence also. So the question is the gap delta between two concentric cylinders, each of height h, is filled with an oil. The torque required to rotate the inner cylinder at an angular velocity of omega against the fixed outside cylinder is d. The diameter of the inner cylinder is d and delta is very less than d. Now the dynamic viscosity of the oil is given by. So uh, can someone tell me what do we need to use here? Like what concept do we need to use?
Newton's law of viscosity.
Yeah, exactly. So this is a question from Newton's law of viscosity. And most times when they'll be asking you for an expression of dynamic viscosity or the value of dynamic viscosity, then this Newton law of viscosity will be the one which will give you that. So yeah, just try it and we will see if you get the right answer or not.
B, sir.
Uh, did you say B?
Yeah, yeah.
Yeah, yeah, I think you are right, Abhijit. Did everyone get it?
Yes, sir.
Okay. So this is, I guess, again easy. We just need to in the final expression, know that torque is given by force times radius. But first, we will have to calculate the shear stress. So for this, we apply our Newton's law of viscosity, which says that the shear stress is equal to, the shear stress is directly proportional to the gradient of velocity. And in our case here, it will be some, let's say, DUdr, or some length here. And then since they have given this is delta, so we can just say this is mu times u by delta, where u is given by omega times r. So you should know that u is your omega times r, and since they have given it in terms of the diameter, so you can just say that this is omega times d by 2. So then our u becomes omega times d by 2, and the distance between the two cylinders is delta, so this becomes mu d over 2 delta. Now we also know that this shear stress is applied in at the interface. So the surface area which is in contact with between the two cylinders will be the one on which this shear stress is applied. So you can actually calculate force from here, which will be equal to tau times the surface area. Tau we know is mu times omega times d over 2 delta, and the surface area is simply 2 pi RH. So that's the outer little surface area of the cylinder, and then in terms of diameter, you can just write it as pi d times h, because h is the height of the cylinder. So then this becomes mu omega d square h, and there's a pi over 2 delta. Now finally, they have said that you need to, so there is some fixed torque which is applied in order for us to get the cylinder to rotate. Basically, that torque works against this viscous force. So you can balance it and just say that this torque, which is given by F times R, or F t by 2. So let's just substitute force from, and just from the upper line. So this becomes mu omega t square h pi times d by 2. So this is 2 delta times d by 2. So this is d by 2. Now just take everything on the left hand side and keep mu here. Then you will actually get 4t delta divided by pi d cube. So there's a pi here, and d square times d is d cube, and you have this angular velocity omega and h. Right, so this will be your option B here. So that's the final answer to this problem. Okay, now let's move on to this question. So a two-dimensional velocity field is given by 10y cube minus x square y I cap plus 2cx y square j cap. If the flow is incompressible, the constant c should be. So this should not take you more than a minute
C.
or two. What did you say?
C.
Yeah, exactly. Yeah, so I don't think anyone would have problem in this one. I will just write down the property for the formula for incompressibility. So just that the divergence of the velocity field has to be equal to 0. And once you do that, you'll find that there will be one condition where C has to be equal to 5 for then only for x and y it satisfies. So we can just look at that. So this will be 10 times minus 2xy plus 4cxy equal to 0. So that is what 20xy plus 4cxy equal to 0. You can take, yeah, you can take 4xy comma. This is minus 5 plus c equal to 0. Now x equal to 0 and xy equal to 0 is a trivial solution which is not of interest to us. So this is always satisfied when c is equal to 5 basically, or c minus 5 is equal to 0. So that's how you get option C to be correct. Now let's see this one. This is again from fluid mechanics. So let V and T denote the velocity vector and temperature in a flow field. The rate of change of temperature experienced by the fluid particle as it passes through the point x1, y1, z1 at a time t1 is 2.5 degrees centigrade per second. The rate of change of temperature at time t1 at the point x1, y1, z1 is 4.8 degrees Celsius per second. Sorry. The quantity V dot grad of T, so this is the advection of temperature by the velocity field at x1, y1, z1 and t1 in degrees Celsius is. So this one is also pretty easy if you know what how to write the material derivative.
Minus 2.3.
Yeah, this is correct. The final answer will be minus 2.3 degrees Celsius per second. Yeah, if you don't know how to do this, just look at the definition of the material derivative. So this is the material derivative and this is given by the local term or the temporal term plus the advective term. And in the question they have given us that, so okay, maybe just that if you have to find the advection of temperature field, you just subtract the total derivative or the material derivative with the tendency term. And here they have said that the rate of change of temperature experienced by the fluid particle as it passes through point x1 y1 z1 is 2.5. So this is our total derivative or the material derivative. So the material derivative is given as 2.5 degrees Celsius per second, whereas the temporal derivative, so that is the rate of change of temperature at time t1, is given as 4.8 degrees Celsius per second. So then it's just a matter of taking the difference. So this is 2.5 minus 4.8. That will be your V dot grad of T. And I guess you will find that this is minus of 2.3 degree Celsius per second. So that's the final answer. This is clear, is or does anyone have any doubt in this? Yeah, I guess not. Then yeah, let's see this one. This is also very easy. So in a simple quote flow apparatus, the gap h between the parallel plates is filled with a liquid of density rho and dynamic viscosity mu, and one plate is dragged at a velocity of u parallel to itself, while the other plate is fixed. The magnitude of vorticity at any point in the flow is. Anyone?
B.
Uh, no. So there is some shear, right? So if you have shear, you already have a recipe of the flow rotating in a way, and then you get vorticity. So this will not be an irrotational flow. So let me just draw the setup for you guys. You have two plates. In coed flow, you have two plates. One plate is, let's say, fixed, and the other plate is moved with some constant velocity. And here this velocity is, okay, let's say capital U. So what you will see is, if even if you apply this no slip here, uh, the flow here will have the velocity u, and the flow here will have the velocity 0. Right, so there is some shearing between the layers. Right. So if you uh, if you assume that I have some thin string kind of a thing here at time t equal to 0, since the flow is has higher speed here at the top than here, after some other time t1, this thin string will sort of start rotating because of the relative velocities. So this cannot be an irrotational flow. Yeah, so that is B is not correct, but okay. The in coed flow, one thing I guess you guys can memorize is that the flow profile is given by this. So this should not be capital U. Sorry. So the flow profile is basically linear within the two plates. So let's say U as a function of y will be equal to capital U, and if the gap is h times y. So this is I have just defined a linear profile between the two plates, and this is sort of like the solution of the Navier-Stokes equation that you get when you just assume viscosity in the y direction and nothing else. So you just have to integrate twice, and then you'll get this kind of velocity profile. And now if you have this, then calculating vorticity is straightforward. So you can just do a derivative of this with respect to y. So then I guess, yeah, you get this is the final answer. Right. So the right option for this is the u by h, and you can keep this in mind that when you have simple coed flow, then you can have you'll have a linear velocity profile in the horizontal direction. Okay, let's see this one. So a water drains out into atmosphere from small orifice located at the bottom of a large open tank. If the initial height of water column is h, then the time taken to empty the tank is proportional to. We have done this question several times. So I think you guys,
A.
yeah, yeah. That is the right option. Yeah. So time taken will be equal to some root of a square root of h. So that it's this option here. So if you have, so this is also intuitive, right? So I mean, okay, maybe all four are linear, so let's not go there. But we will do a similar question in the coming slide probably, where you have to actually calculate the value of time in seconds for some configuration. Maybe we can revisit the concept there. But for now, let's move on to this question. Okay, this is now from engineering mathematics. So let C be a simple smooth closed curve enclosing the region R in the xy plane. Let C be oriented counterclockwise if the value of the integral y plus e raised to the power x squared dx plus 3x plus cos y dy is 16, then the area of R is. This also you can solve. We have spent some time doing vector calculus in phase 1 of these lectures. Can someone tell me which theorem we should apply here so as to?
Green's theorem.
Yeah, exactly. Yeah, so whenever you see something like this where you have mdx plus ndy sort of, then you should already start thinking about the Green's theorem. So please apply the Green's theorem and tell me what the area of R is.
8.
Yeah, right. So the final answer has to be 8. So I'll do this for people who do not remember the Green's theorem right now. Basically, if you have an integral like this, so this is, let's say, p dx plus q dy. This can be equated to the area integral of dx dy. So that is your Green's theorem, and then you can use that here, and this actually gives you the area of that region R. So for us, P is y plus e raised to the power x square, whereas Q is 3x plus cos y. So then partial Q partial x becomes 3, whereas partial P partial y becomes 1. Then this integral is, so I am not writing the whole integral, but this is the integral here, is given as 16, or this implies that 3 minus 1 times dx dy is equal to 16. Okay, so yeah, so a dx dy, or you can just call it dA per se, and just say that this is 16 by 2. Yeah, upon integrating you'll get that area has to be equal to. Yeah, so please revise Green's theorem, Stokes theorem, and the Gauss's divergence theorem. It's almost guaranteed that you'll get one question from there. In every year's exam, I think they ask at least one question from one of these three theorems, and most of these questions are pretty easy. So, if in case you have forgotten about these, please revisit them and try to solve some questions based on those. So this is another easy question. A steady incompressible two-dimensional velocity field in Cartesian coordinate is represented by some expression here. The coordinate of the point in the flow field having zero velocity is,
B, sir.
yeah, there's nothing much to it. You just have to say that u is equal to 0 and v is equal to 0, and that's where the velocity field vanishes. So if you say that, then basically what you have to do is equate this to 0 and equate this to 0. So from here you will get that y is equal to 3 and x is equal to minus 1.7. So you can expect these kinds of questions also. These are pretty straightforward. Now let's see this one. This is again fluid mechanics. The figure shows a reducing area conduct carrying water. The pressure P and the velocity V are uniform across section 1 and 2. The density of water is 1000 kg per meter cube. If the total loss of head due to friction is just equal to the loss of potential head between the inlet and the outlet, then V2 in meter per second is. So we can apply our favorite Bernoulli's theorem here. And yeah, please do that and tell me the final answer.
Eight.
Right. Yeah, that's a correct answer. So I think there is this one statement in this problem which makes our life easier. So here they have suggested that we take the head loss to be equal to the the loss due to friction to be equal to the head loss. So let's say Z2 minus Z1 or whatever. So then if you have this Bernoulli's equation saying that P1 by rho G1, P1 by rho G plus V1 square by 2G plus Z1 is equal to P2 by rho G plus V2 square by 2G plus Z2. And then maybe on the left hand side I add the loss due to friction. Now since this is an assumption given to us in the question, we can immediately take away the head loss and the frictional loss. Then you just have these two variables, and most of these are known to us. So P1 is given as 130 into 10 raised to the power 3 pascals, and I think we can cancel out G's in the denominator. So P by rho, which is 10 raised to the power 3 again, that's rho, plus V1 is also given to us, that is 2. So V1 square will be 4, and then you divide it by 2 because there's a 2 in the denominator, is equal to P2, which is 100 into 10 raised to the power 3 pascals divided by 10 raised to the power 3 density plus V2 square, which is unknown right now, by 2. So you can solve this, and yeah, I think I'll not solve this. I'll just say that V2 square is some 64 Then finally you will get that V2 is equal to 8 meters per second. Right, so this is just applying Bernoulli's theorem. Yeah, let's see this one. Yeah, so this is what I was talking about. A cylindrical tank of 0.8 meter diameter is completely filled with water and its top surface is open to atmosphere as shown in the figure. Water is being discharged to the atmosphere from the circular hole of 15 mm diameter located at the bottom of the tank. The value of acceleration due to gravity is 9.81 meter per second square. How much time would be required for water level to drop from height of 1 meter to zero point 0.5 meter? So try this one. This this has some calculations, so maybe I can give you guys like 4 to 5 minutes. We have done similar question a couple of times, and remember that this will be proportional to the root of h. Yeah, so just find out how many seconds it will take for this tank to get emptied by half its original height.
Sir, 1666 second.
Uh, no, that's not an option, right? You can see the options.
Yes, sir.
Yeah. So I guess this in this case you are lucky because you have option. You can revisit the calculation.
Okay. 376.
I think yeah, that is the right one. 376 true. What about others? Did they get it?
Doing so.
Okay, okay. Maybe I'll wait for yeah, I'll wait for 1 more minute, and then we can actually solve it one more time because I don't know. I have seen this question coming quite often, at least in the engineering sciences paper. So this might be important. So did you get 376, Priyanka?
Yes.
Vijit, you got it. Great. Yeah. So let's see this one more time. So I think we have done this analysis a couple of times, but so I took this from one of our last class directly. I just draw this here. Maybe this is our capital H. This area is capital A. This area is small a. So again, when you do this kind of analysis, you can just take the use of this mass conservation and say that in the control volume, the mass coming in is 0, but mass going out is something which is going out from here, and that is the rate of change of mass. And here we write that the mass going out is just given by rho, the density times the area of this orifice times the velocity, where this velocity you can get it from Bernoulli is just root 2 g h, where h is some variable height which depends upon time. So h is a function of time for this. Right, so you can maybe have that here. H is a function of time. And yeah, then you can say that this dm dt is equal to d by dt of this rho times a times. So now in this volume, rho times a times this h, where h is again a function of time. So rho and a can be taken out, and then you get this differential equation dh dt is equal to a times dh dt is equal to small a, which is here given as a naught, times root 2 g h. Now this is just a matter of integrating between your original height, let's say h1, to your final height h2. And notice here we have a negative sign because the height is decreasing, so time cannot be negative. And then the time goes from the initial time, so at the start it was 0, and then this t is what we want to find. So that's the final expression. And if you integrate, you can take this out 1 by root 2 g minus of that a over a naught, and this becomes root of h divided by, so this will be I guess 1 by 2, and this h goes from in this case, I think in this case it goes from 1 to zero point 0.5. So this is our initial edge and this is our final edge. Now one thing we can notice here is, okay, this is indeed going as okay, yeah, this is t minus 0, so we can just write it as t. So from here we can observe that t is proportional to root of h if all the other variables are constant. So that answers our one of our previous questions. And now it is just doing calculation. So here it is 2 times root 2 into 9.81, and let me see what the diameters are. So it is 0.8 here, and the small one is 15 mm. So I'm not writing pi, I can just write capital D square over small d square. So zero point 0.8 over 0.015, because the A naught diameter was in mm, I'm just converting it into meters. So that will be the ratio of your heights, sorry, area of cross section, and then this will be equal to root of zero point 0.5 minus 1. And this will be your d, and I think if I have done this calculation right, this should be equal to some 376. Let me just verify this. Yeah. So then time in seconds you get is 376. Hey, you can keep this analysis in mind and do similar kind of things. If instead of having the tank filled to half, it is h by 4, h by 6, or whatever, some value. Okay, let's see this one. The velocity potential for an incompressible flow field, fluid flow is given by phi is equal to 2x square plus 2y minus y square. Assume the value of stream function at the origin to be 0. The value of stream function at xy equal to 2 comma 2 is. So this I think you guys can solve. I'll wait for you to tell me the answer.
Archer.
Yeah, that's right. So did someone else get it? Avijit, Priyanka, Syed.
Sir, I'm getting -2.
Uh, yeah, that is not correct. I think 8 is right.
8, sir.
Yeah, Priyanka.
Doing, sir.
Okay. So what you have to apply here is first of all, from the potential you can get the velocities. So this is given by this formula.
Yes, sir.
Yeah.
Did applied same.
Okay. Good. So then you'll get u as 2 times x, whereas v will be equal to 2. Oh, this there will be a 2 outside. So 2 times x. So basically 4x I can write it as 4x power.
Yes, and now got it, sir.
Oh, you got it. Yeah.
Yeah.
So anyway, let me just complete this. So for VE, you will have 2 times 2 minus 2y. Okay, you can write it as 4 minus 4y then. And now, if you have u's and v's, you know the potential, the stream function is defined such that u is equal to minus I minus, oh, yeah, minus I minus y, and v is equal to minus I minus x. So then you can integrate and get psi from here. So which will be a function of x and y. You have to integrate this partially and this partially. And once you get that function, you just substitute psi at 2 comma 2, and that will be equal to 8. So you can do the calculation for yourself. That's how you basically approach this. Yeah, if you have solved this, then tell me the answer to this one. A cube of weight W and and side A falls at a constant speed in medium as shown in the figure. If the medium is air, the velocity is u of u underscore air, and if the medium is water, the velocity is u underscore water. Now, neglecting the buoyancy force and assuming drag coefficient to be same for both cases, the ratio of velocities is given by. So you need to know the formula for the drag force.
C, sir.
Right, yeah. So, yeah, C is the correct option. Basically, if you know the formula for drag force, this becomes straightforward. So, this is half of CD rho A V square. And they are saying that if we assume that there is no buoyancy for and assume that the drag coefficient is same for both, so CD for air as well as your water is same, and since it is falling in the at a constant speed, then this mass balance, sorry, the force balance has to hold that W, which is in the downward direction, has to balance the drag force, and then I guess you could just say that, yeah. So you can divide it. You can divide WFT of air, and since the mass does not change, this is FT of water. You can equate FT of air and FT of water, and then that means that rho times V square is equal to rho times V square. So this is air, air, water, water, and yeah. So okay, we have to write it as U time U of air divided by U of water. So this will be square root of rho of water divided by rho of air. Right, so then you get C is the right answer. Okay, so very similar question. Now you actually have to do the calculation for this one. So 2.6 gram smooth table tennis ball has a diameter of 38 mm. Density of air is 1.2 kg per meter cube. Neglect the effect of gravity. Take the coefficient of drag as zero point 0.5. If the ball is struck with an initial velocity of 30 meter per second, the initial deceleration in meter per second square is. So did someone get the final answer?
117.7.
Yeah, yeah, great. Yeah, that's the right answer. Good, good, Satyam. So the idea is very simple, and since there is no gravity, so you will not have the weight now, and if the ball is struck with an initial velocity of 30 meter per second, because of the drag, it will face some deceleration, and you can say that this drag force is equal to m times the mass of the ball times the deceleration, and you know that the drag force is actually given by the formula half CD rho A V square. So here rho is the rho of air, and A is the area, surface area of the spherical ball here. So you can just say that A will be equal to 1 by 2 times m, where m is the mass of the ball, which is 2.6 grams, times CD rho AV square. So if you do that, then you will get acceleration to be some 1.7 meters per second square. So I leave the calculation up to you guys. Uh, but this is just knowing about the drag force and the formula for drag force. That's all. And we have this question. This is okay. Again, to boost your confidence, nothing else. You have the velocity field given by this. The vorticity of the fluid element in the field at 1 comma 2 is. So the vorticity is given by this. This is in two dimension. You will only have vorticity in the z plane, which will be equal to. So you can just take the dot with the k vector.
Four.
Yeah, right. Yeah. So you can apply this formula and then finally put this at 1 comma 2. Then you get 4 is the final answer. Okay. Yeah, I think so. Finally, if someone has any doubts for one last time, they can ask me.
No, sir.
Okay.
I have some problem on production and meteorology actually facing the problem to face
Hmm.
those kind of questions.
Yeah. So I don't know. I don't think you will have lot of time to
Uh,
yeah
yes, sir.
cover the concepts now. I will just suggest keep on doing the question, and while doing the question, if you encounter some new concept, try to grasp it as quickly as possible.
Mhm.
But for this week, just solve questions. That will be my advice to you guys. And please, when you go to the exam hall, be calm. Don't be stressed. If you are stressed, you will make mistakes, and that is very detrimental to your final score. So please try to be as calm as you can be. Read every question properly. Read about all the input data. Note down all the input data. And finally, when you are solving it, few things that you should always keep in mind is whether it is radius or diameter. So sometimes you think the question the radius is given, but it is actually diameter, and then you can commit a mistake there. And also in the final answer, in the numerical answer type question, in what units they are asking you to write down or type the final answer. So these are some of the most common mistakes that we make when we are writing the gate exam or any test series for preparation of gate exam. Just keep these things in mind, and I'm sure all of you will do great. Just be confident and don't take too much pressure. So that's all I have to say, and I wish all of you guys all the very best. And yeah,
Thank
this
you, sir.
is yeah just one exam, guys. So don't even if you can't perform too well, just don't take it personally. You will get many more opportunities
Yes, sir.
to do great. So yeah,
Thank you.
that is my advice. And I think all of you guys have my email ID. In case,
Yes, sir.
yeah, I'll just write it down here again. So in case you have any feedback, any suggestions, or you just want to inquire about admissions, you can just drop me a mail. If I have time, I will try to reply to you. And yeah, so that's everything I have to say from my end. If you have any doubts or anything you want to say, you can just unmute and just tell me.
Yes.
All right, so I think we are done now. Uh, Again, I'll wish you guys good luck, a good weekend,
Yeah.
and all the best for your exam, guys. Bye.
Many thanks, sir.
Yeah,
Many thanks.
yeah, and thanks for attending these sessions. That this has been yeah, good experience for me. I hope it was good for you guys also.
Yes, sir. We'll miss you, sir.
Okay, bye, bye, bye.
Thank. Bye.
Thank you, sir.
Yeah.